Good afternoon, guys. This is Professor David J. De Los Reyes. Okay, I got a new topic on my channel for this afternoon under the course Differential Equation. I will now be giving you example problem on the evaluation of a Bernoulli's equation. Okay, let's proceed. The topic for this afternoon is the solution of a Bernoulli's equation. It's either case number 1 or case number 2. Okay, let's proceed. This is now lesson DE 27 on my topic, third course, differential equation. The subtopic is Bernoulli's equation. And I will now give you an example problem on how to evaluate the Bernoulli's equation. So I will try to read the problem. The given differential equation is dy dx minus 3 over x times y equal to 1 over x times y cubed. The given equation is a Bernoulli's equation. If I will try to cover y cubed, this is a magnetic eraser, guys, so it connects to the board. If y to the cube is missing, we could solve immediately for the solution. And the solution is by using an integrating factor. But since there is a y cube over here, still for the meantime we cannot solve the problem without using the concept of Bernoulli's equation. And the concept of Bernoulli's equation is that we needed a required substitution. Okay, let's proceed with the solution. The problem is asking for GS. I got a viewer last night, he was asking for the meaning of GS. The meaning of GS under differential equation is general solution. Okay, so the requirement for the problem is find the GS equal to, I place it here, guys, GS is general solution if we are on the topic differential equation. Okay, let's try to bring out the solution. The given differential equation is similar. This is a symbol for similar. This is dy dx plus p of x times y equal to q of x. And for it to fall under Bernoulli's equation under case number 1, there's a y to the n. And that y to the n is actually y to the third power. So actually this falls under case number 1 under Bernoulli's equation. And the required substitution is we identify the value of n. The value of n is actually 3. Okay, so the value of n is 3. The required substitution is this one. It is actually z equal to y raised to 1 minus n. Right? I give you this one on the concept of the solution the last time around under the lesson number 26. So if we try to follow this, z now will be equal to y raised to, we now know n to be 3, okay? It is y raised to 1 minus 3. This is y to the negative 2. We bring it down to eliminate the negative exponent. Z now will be equal to 1 over y squared. So this is the relation of z, the new variable, as a function of y. Okay? Let's try to compute for the value of y. It is just an algebraic manipulation. Y squared can be equal to 1 over z. Okay? Coming from this. Taking the square root of both sides, the square root of y squared is just y. And the square root of 1 over c is just the square root of 1 over c. And y now will be, the square root of 1 is either plus or minus 1. Z, we could put it underneath and it will become the square root of z. Because the square root of 1 is just 1 and the square root of z is just the square root of z. So y as a function of z is actually 1 over the square root of z. We needed this relation here because we will try to bring out dy. Okay? So differentiating this relation of y as a function of z, so we could solve for dy. So taking the differential of the left hand side, dy equal to 1 over the square root of z, it is, what do you call this, a special formula, but for me, I will try to use the power formula, so I will bring it out. So actually, y can be written as z to the negative 1 half. And if I will try to take the differential, I will use power formula. So it should be n times the value of z, minus 1 half plus 1, minus 1 will be negative 3 halves. We are differentiating, right? dy will be equal to, this is z raised to n minus 1. Okay, so minus 1 half, minus 1 half, minus 1. What is minus 1? It is minus 2 halves. Okay, minus 1, minus 2, that will be minus 3, all over common denominator 2. So this, what will come out will be z raised to the negative 3 halves after the deduction of negative 1 times the z. And if we try to avoid the negative exponent, we bring down this one. So dy is actually negative dz, this negative, over 2. This 2 here is underneath, times z raised to the 3 halves. We avoid the negative exponent, so we bring it down. Also, that's the value of dz. And what's the significance of this dz here? Or dy rather. We need a dy here, we need ey here, and we need ey here. So we will put back the value of the computed value of dy, y back to the original equation for the resulting equation to be solvable. So substituting. But I will place it here, guys. This is new. Dy over dx can be written as dy times 1 over dx, right? Right? So this part here can be written as dy times 1 over dx minus 3 over x times y equal to 1 over x times y cubed. Why I segregated it? Because I will try to place the value of dy, okay? And the computed value of dy is actually negative dz over 2z raised to the 3 halves. So I will take this value here, I put it here. So this is the value of dy times 1 over dx minus 3 over x times the value of y. But what is y? 1 over the square root of z. See, equal to 1 over x times y cubed. But what is y? This is 1 over the square root of z raised to the 3rd power. We are just following this, but substitute the value of y in terms of z. So actually what will come out here is a function of z and x equal to, we eliminated dy already, because after the substitution and simplification, what will come out will be a differential equation solvable by using integrating factor. Let's try to see if it's really like that. Okay. What's next? This is just algebraic manipulation. If I will try to simplify this one, this is just simplification, guys. It will be minus dz over 2 the square root of z times dx. I just multiply this one, I compress it. But I will place it here. Z to the 3 halves can be written as z raised to the 2 halves times z raised to the 1 halves. Okay? 2 halves plus 1 halves is 3 halves. And z to the 2 halves is just z. And z to the 1 half is actually square root of z. So I put on the bottom, it will be square root of z times dx minus 3 times 1 is 3 over x is square root of z equal to 1 over 1 cube is 1, and z to the 1 half raised to the 3rd power will be z to the 3 halves. It is actually this one. The equivalent of that is actually z to the 3 halves. But I expanded it as simply z times the square root of z. Okay, so I place it here, square root of z times z. There is a purpose why I put the square root of z, because later on I will try to cancel out something, right? So actually, if you notice it, all the denominators for the left and right, it got in the square root of z. So actually, we could cancel this one. Okay? After the introduction of multiplying all the terms by square root of z. Because if you try to expand this one, all terms will be times the square root of z. So actually, we could cancel. It clears up, right? What will happen will be the bottom portion will be the resulting simplification will be negative dz over 2z dx minus 3 over x. The square root of z is gone, right? Equal to 1 over. This square root of z is gone. So what remains on the right is just 1 over xa. And if we will try to put the first one to be dz dx, we will multiply all terms by negative 2z. So minus dz over this times this, okay? Minus, it will now become plus, and this 2z here cancel with this. So what remains on the first part will be a positive dz dx, okay? Negative 3, negative 2 will be plus 6, okay? Times z over x, because we multiply already the second part by this one, equal to the right hand side, it will be, what will come out? Z cancels, right? So what remains is 1 times negative 2 is negative 2 all over x. Okay? After the substitution and simplification, according to the concept of Bernoulli's equation, the resulting equation should be solvable by using an integrating factor, and it falls under case number 1. So the concept of Bernoulli's was correct. Okay? This is actually similar to case number 1 under integrating factor. That is dz over dx plus p of x times z equal to a q of x. Originally under case number 1, this is y. But for the meantime, that y is actually z. For it to fall under integrating factor. Right? To solve this equation here, specify the value of the integrating factor. The integrating factor is actually e raised to whatever p of x that comes out, use it. So the integral of 6 over x times dx. P of x is 6 over x equal to e raised to 6, the integral of dx over x. 6 is constant, we bring it out. So this should be e raised to 6. The integral of dx over x is natural logarithm of x. Simplifying, this should be e raised to the natural logarithm of x to the 6. And if you try to read this one, if you're an engineer, the meaning of this is the antilog of the natural logarithm of x to the 6 is actually x to the 6. Right? You are taking the antilog. So actually, this eliminates e here. So what will only come out for the integrating factor is actually x to the 6. So if we try to bring out the general solution of this one, it will be z. Recall your integrating factor formula times the computed value of the integrating factor equal to the integral of q of x, the right hand side, times the integrating factor times dx plus c. Case number 1 under integrating factor. Okay, so z times x to the 6 equal to the integral of right hand side is actually negative 2 over x, times x to the 6, the integrating factor, times dx plus c. Rewrite this one equal to, we bring out this negative 2 here, negative 2, the integral, x here, 1x here, so what remains is just to the 5th power. So the one inside is the integral of x to the 5th times dx plus c, power formula. So rewrite this one equal to negative 2, power formula, the integral, it will be x raised to 5 plus 1, which is 6 over 6 plus c. But the original variable is actually y, so we will replace all z by its equivalent in terms of y, because the given original differential equation is actually in terms of x and y. But we know z to be 1 over y squared. Okay? Where is it? This one. Right? We are bringing out the original variable. So this will become Z is actually 1 over y squared times x to the 6 equal to negative 1/3 x to the 6 plus c. It's just a matter of simplification. Actually, you could put this one now as your final answer, or if you want to compress a little bit, x to the 6, same as this one, you put it on the left, it will become plus, right? And there is a common factor x to the 6. So the final answer will be x to the 6 common factor times the quantity 1 over y squared. Okay, minus 1/3, we put it on the left, this will be plus 1/3 plus quantity equal to c. That's our final answer, and this is term 2, guys, as GS. GS, guys, is a general solution. That's it, guys. So the concept of Bernoulli's equation was correct, that after the substitution and simplification, what will come out will be a differential equation solvable by using integrating factor. And it was really correct, because after the substitution of the value of dy and y back to the original equation, what comes out is a differential equation solvable by using integrating factor. And we know how to solve a case number 1 under integrating factor. Just solve for the integrating factor, then follow this general solution under integrating factor. Z, integrating factor, equal to the integral q of x, integrating factor times dx plus c. Case number 1 under integrating factor. So after the integration, luckily the integral of the right hand side was an easy one. It's not easy. Well, we are just lucky to be under the power formula, right? Because if it's a complicated thing, that's another story, right? So the final answer, okay, is x to the 6 times the quantity 1 over y squared plus 1/3 plus quantity equal to c. General solution. Guys, the meaning of GS is general solution. From our friends in India, the meaning of GS is general solution. Okay, good afternoon, Los Angeles.